Hi Professor, my name is Edward, full name Edward Letslip Kang, and this is my video presentation for the Smith chart project. I hope you enjoy. I'll go over parts B and D, mainly as those are the core components of the video. However, I will be making references and comparisons to values found in both A and C to aid in my presentation. So I'll start by following the workflow guide that was provided in the Smith chart guide. With question 1, or rather point 1, which is to show how I plotted ZL on the Smith chart. To do that, all I had to do was to normalize the load impedance, and I do that by dividing the actual load impedance by the characteristic impedance or source impedance. That will give us our load impedance of 0.5 plus 2J. So I'm just going to write that up here so we don't forget. So using 0.5 and plus J2 rather, we'll notice that we have the resistance component and the reactant component, and so we simply have to map that on our graph or on the Smith chart. To do that, the resistance component, we go along this axis and we find 0.5, which we find here. And for J2, which is our reactive component, again, because it's plus, this will just mean go up in the inductive region. We just look for a 2, our 2 is right here, and follow that down. Same thing here, follow this up, and we look for the intersection point, and this will be our ZL, or our normalized ZL. So now that we found that the intersection is our ZL, all we need to do, or the next step, is to show the constant S circle for a ZL. To do that, we simply take the radius, or rather this distance between ZL and the origin point O as being the radius of our circle. In this case, our circle is this giant green circle, and the distance between the origin and ZL is the radius for this circle, and that is the constant S circle. In terms of obtaining the reflection coefficient and voltage standing wave ratio, we'll start by discussing the reflection coefficient. To do that, the radius that we initially found here, radius r, can also be measured with a ruler, and this distance is an actual physical distance that we need to keep track of, because we will use that distance to figure out the magnitude of our reflection coefficient. So you'll see over here, we start here using the very real physical value that we found. We'll measure distance, or the distance r, and we'll come to this edge right here, and we will find that our reflection coefficient is actually 0.8, or a little more than 0.8. Over here it's 0.2, which I've written here. And in terms of the angle, all we need to do is we need to follow this line all the way up, and we'll find that it's actually 50, 51, 52, somewhere in that region right here. And again, that's also reflected over here. In terms of finding the standing wave ratio, we can do that by simply following the arc of our circle down. And we'll notice this point right here. This could be our S value. Similarly, we can find the S value simply by using the same method that we used to figure out the reflection coefficient, because as we'll see here, over here, this is also our reflection, this is also our value for S. Over here it says 10. It's a little past 10, so I wrote 10.5 up here. In terms of how to find Z in at the specified distance, all we need to do again is find the radius, follow this all the way up, and then add the, I think, 0.275 wavelength that we were given, and in doing so we will basically follow this entire circle around and end up at this particular position. The distance, of course, is going to be the same as the radius between ZL and 0, and so this spot right here is our Zin value, which I've also written here. In terms of how to calculate this value, if we scroll up real quick, again, this really, the equations are here. I'm just going to go over this and this real quick. So B, since we don't have the wavelength for this particular scenario, all we need to do is multiply B and L. That eliminates the wavelength, Again, because it's 0.275 from the load, meaning towards the generator, we can just kind of cancel these out. And so it becomes 2 pi times 0.275, and at that point it's just simple calculations to derive this equation and then this other equation that we can use to compare. And that should be that. I think that concludes the Smith chart presentation, and I do hope you enjoy, as I've mentioned. And yeah, thank you.